Hi, my name is Max, and today we're going to be doing a little bit of astrophysics. I didn't really know where to start with this topic, so I actually just did a few quantum mechanics videos first. But today I was talking to a friend, and I got an idea on where I think a good place to start for astrophysics would be. And that's kind of one of the most famous examples, one place where people famously have a lot of questions and confusions. I'm talking about black holes. And these things are terrifying, they're awesome, and they really confuse us. So let's get into it. Let's start off with how they form. So before you have anything in a black hole, you start with a star. So an example of that would be our sun. Now we've got our sun right there, and it's the only star in our solar system. It's the majority of the mass, so it's not really affected gravitationally by the planets. I mean, they pull a little bit, but it's insignificant. Something really interesting is out there in one of the orbits we have Jupiter, which is a gas giant planet. Now, something really cool about Jupiter is if it was any larger, it would actually become a star. A small star, but a star nonetheless. That would mean we'd have what's called a binary star system. And that just means two stars, binary. Now, let's pretend Jupiter was more massive and a decent amount more, so it became a star with a decent amount of mass. And let's pretend our sun was much bigger, like just a giant star. So we have two big stars in a binary solar system. Now, what does this mean? Well, we've got two objects of great mass that are attracting each other. Both are obviously in orbit and moving different directions. So we've got an orbit that kind of looks like this, where these two kind of just follow that cycle, orbiting each other. But as time goes on, that orbit will start to decay. Slowly become less, till we get right to the center. Then, kaboom. The two stars explode, and it's incredible. But at the center, you've got an incredible amount of mass, because you've got two stars that just collide. So you've got the mass of two stars, and think about all that gravity. Pulls it all together. And that's how you end up with what's called a neutron star. Smaller than a planet, contains the mass of a star. These guys are incredible. They deserve a video of their own, which I'll do in the future. But just to put into perspective how insane these things are, if I had a coffee cup full of neutron star material, it would weigh as much as Mount Everest. These things are insane. They push the limits, or are the limits, of physics when it comes to like what density materials can handle and just things like that. So you've got a neutron star, and let's make it interesting. Let's put another neutron star over there. Well, what are we doing now? Well, we got a binary star system, so they orbit. And like last time, the orbit decays. And now, you know what happens? An even cooler explosion. Because now you've got these two super massive, but physically not as large objects colliding with insane power, insane gravitational force. Got such an insane amount of mass in such a small area, the gravity shoots through the roof. In fact, it actually becomes infinite to a point because you have so much. What ends up happening is because there's no known forces that will stop the gravity from infinitely collapsing the mass, you get to what's just called a point. And I'm exaggerating it. A real point would have no volume. You wouldn't be able to see it. It's smaller than small. This point is what we call a singularity. That's because it's a single point that contains everything. All the mass of everything, of the black hole, is there. The volume, remember, is zero because it's just a point. So we've got something crazy. volume 0, the mass of the black hole, that doesn't make sense because that means the density would be infinite. And that just, how can that be? Well, short answer is we don't know. But it does have some really cool effects. So one thing you're probably asking yourself right now is, okay, if the singularity is super tiny, no volume, why, and you can't see it, why do we see these massive black holes in movies? Well, one thing of that is cinema, but another thing is that that's not the only part of the black hole. It contains all the mass of it, but there's something more. If you think about it, this point essentially has infinite gravity. But as you get further away, obviously that'll get weaker. So there's a certain point around that singularity called the event horizon. As far as astronomy is concerned, this is like your point of no return when venturing into a black hole. And why is that? So let's draw a stick figure over here. We'll call him Bob. Bob is an astronaut, and he's exploring a black hole. But now he's gotten too close, and he's gotten to the event horizon. What happens to Bob? At this point, at the distance away from the singularity that it is, the event horizon, we've reached a point where in order to move away from the black hole and escape the singularity's gravitational pull, he would literally need to be traveling faster than the speed of light. That's impossible. That means that the gravity here is so strong, it's physically impossible to escape. So, if that's the case, why don't black holes just suck everything in? Well, like I said earlier, it's just gravity. So think away about how planets orbit a star. It's the same way. You could orbit a black hole. As long as you don't travel towards it, you'll be fine. But what causes the event horizon and where do we get the name black hole? Well, let's say we have a photon that's traveling along, and it's going just down that way, just for ease sake. That's our photon. Well, gravity can curve the path of that, because, again, all this is, really, is just a huge distortion and almost a rip in space-time. Now, since photons just travel linearly across space-time in their given path, when this contorts and stretches space-time, the path starts to look more like that, curve. You get close enough to the event horizon, and it eventually will just start to look like that until you get to the singularity. Once you get past the event horizon, no matter which direction you travel, you will always reach the center of a black hole. That is how strong gravity is there. So, if you're worried about black holes at this point, that's a perfectly reasonable reaction. It makes absolutely no sense. And to be fair, everything I've just thrown at you is more or less theoretical. We haven't been to a black hole, haven't been inside one, we don't know what is inside one. I mean, for all we know, there's a whole universe in there. I mean, if you're a subscriber to string theory, which is a whole nother topic of its own for another video as well, this whole idea of a singularity is actually just bogus. Instead, we'll get rid of this model we have here. They believe in what's called a fuzzball. So, in a quick nutshell, string theory believes that all particles, fundamental and elementary particles, are made of what are called cosmic strings that are one-dimensional lines, for lack of better words. And I know I'm using that wrong, so I apologize. That vibrate, and the vibration determines what type of particle it is. Well, when you enter into a black hole and you get past the event horizon, the gravity becomes so strong, string theory can argue that it can break down those particles into just their cosmic strings. So you just have a bunch of strings kind of floating around in a tight nest, kind of like a cosmic fuzzball, hence the name fuzzballs. Is this theory true compared to singularities? I don't know. I personally think they both are very, very sound, and both could be right, both could be wrong. We have no way of knowing yet. I do hope you enjoyed this video. If there's anything you'd like to learn about in the future, let me know. Have a nice day. Thank you.